I will talk about volume of p-zonoids and inequalities for determinants. So I work in Rn with the Euclidean norm and canonical basis and Euclidean ball. I denote by b to n, and the sphere by Sn minus 1, and the volume is volume. And the support function is, you know what it is. It has been defined in previous talk, but this is just the supremum of for A in A of X scalar A. And when A is convex, it is completely determined by its support function. And so I introduce these things to introduce you the subject of my talk, which is p-zonoids. So p-zonoids, what it is, first, Minkowski sum. So the Minkowski sum of two sets, you know what it is, just the vector sum of the point in the set. And here I made a drawing. And also it can be defined via the support function, because the support function of the sum is just the sum of the support function. And as I said, for convex bodies, this determines the set. And now if you have compact convex sets containing the origin, the p-sum, the Minkowski p-sum, I just write the p-sum of A and B, is denoted by A plus O plus with a p down, is defined, the convex body defined by its support function, and is a p-sum of the support function of A and B. Okay, so for p equals 1, you recover the Minkowski sum, and for p larger than 1, this is also a convex compact set, and it was introduced by Fay and developed a lot by Ludwig, who established a number of inequalities regarding this Minkowski p-sums. Okay, and so I'm interested in p-zonotope and p-zonoids. So a p-zonotope is just the finite p-sum of segments. So like this, so this is a p-zonotope. It can be written as a finite p-sum. So there is associativity of the p-sum, so I can put just without parentheses. And this is this way. And so it's because of the definition of the p-sum is the same as saying the support function of z is just the sum of this scalar product, because the support function of a segment is just scalar product, absolute value of the scalar product if the segment is symmetric, which is our case here. And so we get some LP norms, if you want, like this. And for p equals infinity, you can get the max. So what happens if you start with the canonical basis, minus E1, E1, and you p-sum it to itself, so minus E1, all segments of the canonical basis. What do you get? And you just check. Hz is the sum of xi, absolute value of xi to the p, to the power 1 over p. So this is a p norm, but because it was a support function, this is in fact the norm of the polar. So what you get when you do this p-sum, you get in fact the polar of the LP BPN, which is a BQN for 1 over p plus 1 over q equals 1. So it's a bit mixed, and you need to be careful when you write these things. And so, for example, when you have the one sums of the segments built from the canonical basis, you get the cube. And if you took the infinity sum, you would get the L1 ball. Very good. So now, what we call a p-zonoid, this is just the Hausdorff limit of p-zonotopes. So it's the same as saying here, you had a finite sum. You can replace it by an integral with respect to some positive measure of the same power and power 1 over p. Okay. And so I arrive to the question I'm interested in. I am in dimension n larger than 2. I take any p larger than 1, and I have A and B, which are p-zonoids in Rn. And I denote for u unit vector, pu is the orthogonal projection onto u perp. And I ask if this inequality holds. So this inequality says that the volume of the p-sums of A and B, recall that A and B are p-zonoids, to the power p, divided by the n-1 volume of the p-sums of the projections, to the power p again. Is it larger than the volume of A to the power p, divided by the volume of the projection of A to the power p, plus the same with B. Okay, so this inequality I call 2 star. And there is a weaker question is without the second term. So then you can take out the power p's and you ask if you have two zonoids, p-zonoids, do you have this inequality? So the first one could be called like some p concavity, and the second one could be called monotonicity. So when you add p monotonicity, when you add a p-zonoid to a p-zonoid, does this ratio increase? Okay. So what's known about these inequalities and why we bother to look at it? So in fact, it comes from, like almost 100 years ago, Bunsen proved the first star in the most elementary case, which is p equals 1 and n equals 2. And in fact, in this case, for p equals 1 and n equals 2, it's true, this star is true for any A and B convex, and not only for A and B zonoids. Because you remember that for me, I asked if this inequality holds for A and B being p zonoids. For p equals 1, these are just zonoids. And zonoids are equal in R2, because here Bunsen is in R2. Zonoids in R2 are just centrally symmetric convex bodies. So, in fact, Bunsen proves that this inequality holds even if you don't assume that the bodies are centrally symmetric. For any convex bodies, this inequality holds in dimension 2 for p equals 1. Okay. So what we know, of course, 2 star implies 1 star. Okay. So what we know for p equals 1, we know something else that was proved by Giannopoulos, Artsoulaki, Paris. And in fact, they prove that star cannot hold for any convex bodies in Rn, for n larger than 3. So in dimension 2, 2 star is true for any convex bodies. This explains why I restrict to p-zonoid. In dimension 3 or larger, it's not true, even star, so also 2 star, is not true if you want to have it for all convex bodies. So this is why we restrict ourselves. So with this talk I'm giving is exposing results I have with Mokshay Madiman, Matthieu Meyer, and Artem Zvic. And so we have some positive results. So star holds for p equals 2 in any dimension. So I come back to star. So this is true for two zonoids, A and B, two zonoids, and you put power 2 and you have two zonoids, two sum. This holds, okay, in any dimension. Good. Also, just 1 star, it's true for p equals 1 and n equals 3. So far, we cannot get outside this dimension 3, and so we can prove only this one in dimension 3 and only in dimension 3 for p equals 1, so for usual zonoids. So what now the negative results? So when we are sure that it doesn't hold, so first, 1 star doesn't hold for p strictly larger than 2 in any dimension. So also 2 star doesn't hold. So here I wrote it as a question for any p larger than 1, but we already know the answer. So the answer for p larger than 2 is that it's not hold, it doesn't hold. So we know that doesn't hold for p larger than 2 strictly. And we know, again, like Giannopoulos, Artsoulaki, Paris, that it's useless to pose a question for any convex bodies in dimension larger than 2 and p strictly larger than 1. So it's different. This says that the case p larger than 1 strictly is different from Bunsen. Bunsen was true for any convex sets in the plane. This and p equals 1, this inequality holds for any convex set. Even this in the plane for p strictly larger than 1 does not hold for any convex set. The second inequality, the weaker. Okay. So now I wanted to show you 2 proofs we have for the case p equals 2. So So the case P equals 2, so we have two zonoids. So the first proof is using linear algebra. So using linear algebra, what we can say? So we have A is, I recall, this is L2 sum of, we stated it for, I stated it for two zonoids, but of course, two zonoids are just a Hausdorff limit of two zonotopes. So it's enough to prove it for two zonotopes. So let's prove it for two zonotopes. So A is just the two sum of segments, and B is the two sum of segments. So here I assume I did the case where we have more than n segments, and also for B, so that they have not zero volume. So if they both have zero volume, of course the inequality holds. If one of them have zero volume, the inequality still needs to be proved, but you can prove it with, first you prove this, and then you go to the limit, and you will get this. So I can assume first, and I will assume, that volume of A is not zero and volume of B is not zero. Okay. And now I introduce this matrix. So this is a long matrix with all vectors that appear in A and B. I put in columns, U1 until UM. So all vectors. So this is a long rectangular matrix, and it's like an operator for Rm to Rn. Okay. And then A plus B, the L2 sum of A plus B, is just U times B to M. So the big space, and you send it in Rn. And it's to see that it's the same as star B. So small space. And because of this formula, volume is just the volume of B to N times the square root of the determinant. I hope you hear me.
Yeah, now we hear.
And then, yes, it's okay?
Yeah, now it's okay, yeah. We lost you for 2 seconds.
Yes, it was saying it is unstable. Okay. So this determinant of U star is exactly, in fact, the Gram matrix of the vector Z1, Zn, which are the lines of U. So now you introduce Z1, Zn, which are the lines of U, which are vector in Rm. M is big, you remember? So you have a smaller number of vectors in a big space. And U star is just this scalar product, which is called the Gram matrix. And it's well known and well studied and explained in small classes in university. And it's well known that the determinant of this Gram matrix is just the volume of the parallelotope defined by these vectors, the sum of 0 zi to the square. Okay. And so, because of these two formulas, we have now a formula. Our matrix, volume of our two zonotope, volume of A plus 2B, is just up to a constant, which is just the volume of the Euclidean ball of radius 1, times the volume of this parallelotope. And the parallelotope was the parallelotope built from the lines, the whole line. Okay. And now I haven't said, yes, I'm sorry. So let's go back to the formula we want to prove. And we want to prove for any U, vector U, but of course, everything is rotation invariant. And I can assume in this formula that I will take U equals En, the last vector of the canonical basis. And so because I'm looking at U equals En, when I'm looking at PUA and PUB, I'm just projecting PENA. And so it means I'm canceling the last, I'm putting 0 in the last coordinate of the vector, because PUA is just the sum of the projections. The projection of the sum is just, there is linearity also with the two sums with respect to linear operator. So PUA of A is the sum of the projection of each segment, and the projection of each segment is just taking a 0 as the last coordinate. So it means, with respect to my matrix U, I'm canceling the last line. Okay. So if I compute this, the same, I can apply the same formula here for the volume of the projection. Projection of A plus projection of B is the same, but I'm canceling the last line. So I get volume the same, but with n-1 line. So I get this constant times the n-1 volume of this parallelotope, which is the same, but I take only one vector less. And so now if I introduce the span of these vectors, z1, zn minus 1 in Rm, so the big vector space, what I am looking at, it was, you remember the quotient of volume of the volume of A, the L2 sum of A and B divided by the volume of the n minus 1 volume of the L2 sum of the projections. So I just divide these two lines. So I get a constant, and when I divide these two lines, I get a constant, and then I get the quotient of the volume of these two parallelotopes. But you notice that the second parallelotop is just a face of the first one. And so I get that this quotient is just the distance, because you know the formula for the volume of a parallelotop. You can write this is the volume of a face times the volume of the height. And the height is just the distance between the n and the hyperplane here. So we get exactly this formula. And if I plug in what I said, I get this constant, Cn, let's say, times this distance from the n, the last vectors that I cancelled, to the other, to the plane built by the other vectors. So this was true for A plus 2B, but it's the same with A and the same with B. So with A and B, I recall, what was it? I come back a bit, sorry. A and B, here, it was the same as A plus B, except that they are the first vectors of U, and the first columns of U, and then it's A, the first K column of U, and the last ones are B. And this is how are built A and B. So you can see it as projections. So you can see that the same applying the same formula, you get that volume of A divided by the volume of the projection. It's just the same constant Cn times the distance of the projection. So I introduce the subspace of Rn generated by the first K coordinates. So the distance of the projections of the n to the e to the projection of Hn to e. Projection of Hn to e meaning Hn is the span of z1, zn minus 1. This is the span of the projection of on E of z1, the projection of E onto E of zn minus 1. Okay? And for B, I have the same. And so we just need to prove that the distance from Zn to Hn to the square is larger than the distance from its projection to the projection of the space to the square plus the distance of the projection to the same with the orthogonal. And this is very easy because you just introduce the point in Hn reaching this distance. And by Pythagoras, you know that this square is exactly the sum of these squares, and the projection, the norm square is the sum of the square of the projection to the space and to its orthogonal. And by definition of this distance is larger than this. And so you get the result. Okay, so this was not difficult, and we just use two formulas. If I come back, we use a formula for the L2 sum with square root U star, and the gram matrix, the gram determinant formula, which translate to parallelotops. And then with parallelotops, the inequality we need to prove is direct from Pythagoras. Okay, and now I have an even shorter proof that we found, and we use geometry of ellipsoid. So what we use is that, in fact, it's a bit strange, but pzonoids, if you look at it, let's come back maybe. I'm sorry, I'm moving up and down, but okay. Let's come back to the definition of p-zonotops. P-zonotops was like this. And if you put p equals 2, so this is sum of quadratic forms to the power 1/2. So the square of the support function is a quadratic form because it's sum of quadratic form. And so the support function, being a quadratic form, is just the support function of an ellipsoid. Okay, so all pzonoids are just ellipsoids. Maybe if you sum less than the dimension of segments, you can get the smaller dimensions ellipsoids. Okay, And so if you have an ellipsoid, you have a nice relation between the volume of the projection of this ellipsoid and the volume of the ellipsoid. And let's check what it is. So the volume of the projection you can recover with the mixed volume. So you all know what is the mixed volume. So first, ellipsoid you can write as a linear image of the Euclidean ball. And so the volume of the projection is n times the mixed volume of E taken n-1 and the segment 0u. And then you replace E by Tb2n, and you factor out T because of properties of mixed volume. You can factor out T, and there is determinant of T which appears, absolute value of determinant of T. I'm sorry. And because you have factor out, you have B2n, and here you have T-1u. And now you recognize again that it is this n times this mixed volume is a projection. Orthogonal is norm of T-1u times the projection of the Euclidean ball on the perp of T-1u. But the projection of B2n-1 is just a Euclidean ball of dimension n-1. So you get the absolute value of determinant of T times the norm of T-1u times the volume of the one-dimensionless Euclidean ball. And now this norm of T-1u is the same as norm of u in the norm defined by the ellipsoid. And now the quotient we are interested in is just volume of the ellipsoid divided by the volume of the projection. So you just divide this volume of the ellipsoid. Volume of the ellipsoid is just determinant of T times volume of the Euclidean ball. You replace, determinant of T cancels out, and you just get this constant, which is the same as the constant I had before, which is nice. So this constant Cn, if you want, times the inverse of this norm, and the inverse of the norm is just the radial function. The radial function, so here I wrote on a picture what it is. So this is just the inverse of the norm. So this quotient that we are interested in is just a constant times the radial function in the direction u. So what we want to prove is just we can cancel the constant which appear on both sides, and we just want to prove that the radial function of a Minkowski two-sum to the square in direction u, I didn't put, is larger than the square of the sum of the radial function. I mean the sum of the square, sorry, of the radial function of each ellipsoid. But this is the same as saying that this Minkowski sum and Minkowski two-sum contains the radial two-sum. And this is not difficult to check, and it's well known from the work as I said, of Luttwak, who studied a lot this kind of sums. I mean, this is, yeah, maybe it was also known from Fire. Okay. So this proves this inequality. And now I have just a few minutes 1 minute, let's say, to show you a last conjecture, which is very related, in fact. So you can look, you take capital M vectors in Rn, and you look at the projection again on E1 perp. And then I call 2 star prime this conjecture. So the sum of all determinants I can build from cardinality of I equals n of ui to the power p times divided by the sum of all determinants I can build with cardinality of I equals n-1 of the projection of ui to the power p. Is it larger than if I truncate and I look only at the first vectors and I look at the same quotient, and plus, and now I look at the second half of vector and I look at the same quotient. Okay, so I ask if this inequality holds. So in fact, this inequality may look strange to you, but for p equals 2, because of Cauchy-Binet formula, we recover exactly the same inequality we had before. Because some of the determinant of u star I didn't write it, but it is exactly this determinant with p equal to. And so we know it's true. This inequality holds always in all dimensions if p equals 2. Again, we check that for p larger than 2, this is false. Even this is false without a second term. And for p equal 1, the same conjecture. This is for p equals 1. Again, this is the same. I haven't said it, so I say it now. For p equals 1, this is the same. This sum of determinants is the sum of the zoonoid generated by the UI. For p equals 1, this is sum of 0 UI. And so this is exactly the same inequality I was asking for. And so in dimension 2, it's true, but by both. And I said, so star prime, which is an inequality without the second term, is false for p larger than 2, and is true for p equals 1 and dimension 3. And for p between 1 and 2 strictly, this is a different conjecture. It's known that the volume of the p sum of segments is not the sum of the determinant. For example, it was studied in a paper by Gordon and Joram Gordon and Junge, Marcus Junge, the relationship between this, the volume of the p sums and the sum of determinants. And they proved the optimal constant bit for this inequality. So I think I am out of time, and I need to thank you for your attention.
Okay, let's thank our speaker, Matthieu.